Hey, welcome back, biophysicists. Today, I'm happy to have on the show with us Ondrej. He's a researcher out of New York, and we're going to be discussing the recent paper on Brownian motion and cross-linking kinetics and actin networks. Ondrej, thanks for being on the show.
Thanks, Clark. Thanks for having me.
Yeah, so why don't we just go ahead and dive right on in then. What kind of got you interested in this?
Well, as long as I can remember, ever since my undergrad, I was always interested in cell division and what is the mechanical process that drives cell division. And so that was sort of my first idea for my PhD thesis. And then the first thing that we said with my advisor was, well, why don't we just start with actin and crosslinkers? And I guess we didn't realize how interesting just that would be. And so then we started looking at actin and crosslinkers, and we wanted to study morphology. And we realized that if you just have actin and crosslinkers, these bundling dynamics happens. And so that became a paper on its own of what drives bundling. So that's really how I got interested, from cell division to actin and crosslinkers to just looking at a movie and seeing these filaments come together in bundles, and then trying to understand what are the mechanics of that and what are the parameters that control that.
Yeah, so I guess maybe we can even take a step back then. So do you want to kind of set the framework for what exactly actin is, what's its role in the cell, and why is it an interesting problem to even try and tackle?
Right, so actin is kind of like the scaffolding of the cell. We talk about the cytoskeleton. That's kind of like scaffolding. Here in New York, I mean, there's scaffolding everywhere, right? It gives people climb on it, it gives it its structure. Just like that, materials in the cell are transported along the scaffolding. And it's more densely concentrated along the boundary of the cell, but in the interior, there still is this gel. And there's sort of three components to it. There's the actin filaments. Well, there's other types of filaments, but there's the actin filaments, there's crosslinkers, and then there's motors. So motors are different from crosslinkers because they pump energy into the system. They're active. Crosslinkers, the ones that we consider, are passive. And then you have filaments. So there's three kinds of filaments in the cell. The first kind are microtubules, which are long and stiff, kind of like rigid rods. Everybody knows those because they make up the spindle. The second kind is actin filaments, which are so-called semi-flexible. And they're interesting because they're not rigid, but they're not like worm-like chains like you learn about in polymer physics. They're some kind of hybrid of those two, where they can bend but not a lot. And they have smooth shapes. And then the third kind of filaments are intermediate filaments, which are usually very flexible. So they go into these weird worm-like chain configurations.
So the cell needs more or less all three of those kind of building blocks in order to do all of its different functions. And you're particularly interested in just one subset of this?
That's right. Yeah, so it needs all three. And why actin? Well, actin is important because it gives the cell its structure. So when the cell divides, right, these actin filaments, they line up along the boundary in a contractile ring, and then they pinch. So that's how the cell divides. So the first thing that we wanted to look at was, how does this process happen? And I mean, it's more complicated than just the filaments lining up. There's motors that drive it. But, in the end, to understand division, you have to understand the cytoskeleton. And you have to therefore understand the ingredients of the cytoskeleton, starting with just actin and crosslinkers. And even as an in vitro system, that's interesting, right? There's been a lot of experimental papers. This paper was in fact inspired by two experimental papers on bundling with just actin and crosslinkers.
Yeah, I mean, that's interesting. It's definitely like the stereotypical physicist reductionist viewpoint, right? You just keep going down and down until you get to the simplest possible thing to study. But it's still interesting.
Yeah. I mean, I suppose, right? I mean, I don't like to think of myself as a physicist. I'm a mathematician, right? My PhD is going to be in math, but in math we'll say, oh, physicist this, physicist that. So I try not to think of myself that way. But yeah, I mean, we kind of reduced it down to just a couple ingredients of the system. And then there's always the question of, well, if the macro system has these properties and these ingredients can't explain them, then what's missing? So
Okay,
that's
so we
kind of
talked
a
a
way
little bit
of-
about the actin, but it's not just actin that you're modeling, right? What are the other kind of agents or characters in this narrative that you tell?
right. So there's really just two agents. So there's actin, which are semi-flexible filaments, and then the other agents are these passive crosslinkers. So in real life, they're these tiny. You can just think of them as dumbbells, basically, right? They'll have a head, a tail, and then a little rod connecting them, maybe a spring, and they're gyrating back and forth. And then they just diffuse around by Brownian motion, and they define these filaments. And once one end binds, the other end is like diffusing around, looking for another filament, and then it binds it. And so what we did was we kind of reduced that down. So we are looking at, like, we have a master's student in our group who's looking at that actual process and trying to kind of estimate macroscopic rate constants from that diffusion. But what we did was we just assumed, we don't actually model them as individual agents. We just say, okay, if a pair of filaments is close enough, we'll bind them with a crosslinker with some probability. And so that's how we simplify the model. But it's still agent-based. So it's still, if you know the Gillespie algorithm, we still have an event-driven simulation where there's some rate where these crosslinkers combined, and that rate kind of is supposed to account for the diffusion-limited process of them diffusing around.
Yeah, that's interesting. So you more or less kind of abstract away one of the characters just by having some distance cut off that you assume a reaction to occur in?
That's right. Yeah.
Okay, so in terms of this agent-based modeling, what are the kind of key components that you need in order to build this from the ground up? So, you have to have dynamics, you have to have structure. How do you go about putting those pieces into the puzzle?
Okay. Yeah. So this is my favorite part. So you start with filaments, and we model them, and this is different from everybody except one paper that I know of. We model them using a spectral method. So most people, when they model filaments, they just put a chain of beads. Our method is more efficient because what we do is we model the filament as a continuum curve. So it's just, you have some curve x, which is a function of arc length s, and you sample that curve at Chebyshev points. So that's why it's called a spectral method. It's spectrally accurate in a number of points.
Do you want to say a little bit about what Chebyshev points are?
Right. So Chebyshev points are, if you think about doing interpolation, just polynomial interpolation on the interval -1 to 1, right? Chebyshev points are the points that you put down that gives you an interpolant that gives you exponential convergence. So if you have n is the number of points, you're trying to approximate a function. You're looking at the rate of convergence as you add more and more points and more polynomials. The Chebyshev rate is optimal in a sense. And what it actually means in practice is that instead of a uniform grid of points, you cluster points closer to the boundary.
So you're more or less kind of putting the points where interesting things happen.
That's
Because
right.
if you have these actin that are semi-flexible, the middle's probably not really going to bend too much, right? The ends are probably where most of the floppiness occurs.
Yeah, you could say that. Yeah.
Okay, so that's kind of interesting. You take a continuous approach to your filaments.
That's right. Yeah.
So once you kind of define a filament and you have it broken up into these pieces, what do you do next?
Okay, so then there's three forces which act on the filament. The first one is the bending force. So it's just a Euler beam model. So there's the bending force is 4 derivatives of arc length. And then the second one is constraint force, because the filaments are inextensible. So there's a constraint force that preserves that. and that's just a tension. So there's a tension in the filament that keeps it inextensible, and then the constraint force is tension times the tangent vector differentiated. That's the
So
second
this
force.
tension force mostly keeps it from kind of pulling apart like a string bean, I guess.
That's right. Yeah. So the tension, if you think about it, if you take a filament and you try to stretch it out, right? There's a tension in the rod that keeps it from that kind of enforces the constraint that it can't stretch. And yeah, so that's what the tension force is.
And I could use some T-shirts like that. But
Okay.
okay, so what's the third force then?
The third force is the crosslinkers. So once the crosslinkers are bound, they exert a force on the filament. And normally you would think about that as, you have two beads, they're connected, it's just a linear spring. And that's basically what it is. But like I said, because we don't have points, we have continuous curves. We smooth forces out. We don't put delta functions on the fibers. We just put a Gaussian blob. So they're basically smooth spring force. That's what the crosslinkers are.
That's interesting. So do you have a particular bias then for a location that you bind to, or is it just like the closest possible location for the crosslinker and then smoothed out over a Gaussian?
Well, so if you have one end bound, right, the other end is just looking for nearby filaments. And there's no bias as long as it's within a certain distance interval, that other end of the crosslinker can bind to the other filament. And so now you have filaments that are connected to each other.
So I guess once you have these three forces, like you've pretty much done your force balance, how do you weight each force? How do you know that this particular force is not, 3 orders of magnitude higher than the other force? Is this experimentally driven?
Well, no, I mean, so we have equations. We know what the equations are for the force. We know what the equation is for the bending force. We know what the equation is for the constraint force. The cross-linking force, all we don't know is the spring constant. So, and the rest length. So we know that we're going to consider alpha actin. That has a rest length of about 50 nanometers. So that's what we use. And then for the spring constant, we go on the low end. So because we treat the crosslinkers explicitly in our time stepping, we are limited by the spring constant. So the bigger the spring constant, the smaller the time step we have to take. So we just go on the low end of the experimental range, which is 10 piconewtons per micron is the low end. I've seen it as high as 1,000 or 10,000.
So, wow, okay. So it's spreads a couple orders of magnitude then.
Right. It depends. Yeah. I mean, everything in bio is different depending on what system you look at. But I want to emphasize that. So once we have forces, we're not just solving sum of forces equals 0 at every time step. We actually have dynamics. And the dynamics are governed by a fluid. So everything is immersed in a fluid. And the fluid obeys the Stokes equations because we have small length scales. So the Stokes equations are the Navier-Stokes equations with the inertial term eliminated. So you just have mu Laplacian of u minus grad p equals minus f. And we solve those equations on a slender filament using something called slender body theory. And the idea with slender body theory is that if you assume a force along the center line, you can actually figure out asymptotically in the slenderness of the filament what the velocity of the center line should be. And the idea behind that is you take that force, you solve the Stokes equations to evaluate the velocity, and then you compute the velocity along the filament cross-section. And that's how you get the velocity. And you can actually just express that as an integral equation. So you can write that the velocity equals basically the integral of some function times the force.
So I guess to kind of be clear, you're not writing out an explicit Hamiltonian and then just solving this based off Hamilton's equations of motion?
No, that's not what we're doing. So that perspective would be, you have an energy and then you just want to minimize the energy at every time step. Sum of forces is zero. And what we do is we actually have, we have a force on the filament, and then we have a mobility matrix, which gives you the velocity from the force. And that mobility comes from basically solving the fluid equations that govern the fluid motion. So another way to think about it is that all of these forces are exerted on the fluid. And then as a result, the fluid gives some velocity. And that's the velocity at which we move the filaments.
Okay, so you have the filament acting on the fluid acting on the filament, and kind of lockstep with one another.
That's right, yeah. And the last thing is that an interesting problem with that is non-local hydro, right? So if you have two filaments in a fluid, you push on one, the other one moves because of the fluid. And so in this paper, we didn't look at that, because the reason is we looked at it in another paper. And what we basically found was, we found that when you push two filaments together, right, in a bundling process, as two filaments come together, the flows are opposing each other, right? So I'm trying to bring two filaments together. The fluid that's moving is moving in opposite directions. So filament 1 is moving the fluid left, filament 2 is moving the fluid right. So the disturbance flows on the filaments are in the opposite direction of their motion. And so what it does is it slows down the bundling process. We studied that in another paper, so we didn't look at it here.
So I guess it's not a dominant force then, if you can kind of choose to not look at it in this case.
Well, if the filaments are well separated, it's definitely not dominant, right? Because you have this dense suspension of filaments, the flows just cancel each other out, basically. But if you have two filaments that are very close, then yeah, it is important. I mean, we showed that the stress in the system, if you try to make the bundles move, if you don't account for hydrodynamics, your estimate of the stress is off by like a factor of 2. So
I guess this is heavily medium dependent, right? If you move from like water to some type of, I don't know, hydrogel or something, or not a hydrogel, but something maybe like honey that has a higher viscosity, then these hydrodynamic forces become more or less important?
I'm not sure about that, because for the Stokes equations, all the viscosity does is it just rescales time. So I'd have to think about exactly how that works, because you have to remember that we're in a very small length scale, right? And so there's no inertial force going on. And so because of that, all the viscosity does is it just sets the time scale of the motion. You apply a force, the motion is the same no matter if you move in water or glycerol or honey. It's just that the time it takes to move is a little bit slower. Now, in this case, it's a little bit different because there's another time scale in the problem, which is the bundling, the crosslinkers coming on and off. But in principle, those are also diffusing in the fluid, and so they also have a time scale set by the viscosity. So what I would expect in real systems is that the medium shouldn't really matter. It should just set the time scale of the motion.
That's interesting. Yeah, definitely something neat to look at. Is there other maybe external parameters that you could tune that would give you different characteristics?
Well, yeah, I mean, that's what we did in this paper. We looked at, we varied things like the filament length. We varied how the mesh size, so how concentrated the filaments and how concentrated the crosslinkers are. And so our main result in this paper is this phase diagram of the mesh size versus the time that you bundle these filaments together. So we did change a number of parameters. I mean, we looked at changing the viscosity. We've looked at that elsewhere. It wasn't in this paper.
Yeah, I mean, it's always difficult with these types of models. You know, you have a sea of parameters and trying to figure out which ones are important and which ones you can kind of just put a reasonable value for and get something out of it. But I guess kind of jumping ahead then a little bit to the results,
Yeah.
what was maybe not the big takeaway, but what was the first thing that you guys really wanted to look at to see if you could tease out any characteristics from?
Well, the first thing that we wanted to look at was the role of Brownian motion, right? So in the setup I described, the filaments are semi-flexible, but there's no Brownian motion. They're just being moved by the crosslinkers. So if you look at them, it looks like they're diffusing. It looks like there's Brownian motion, but there's really not. They're just being tugged about by these crosslinkers. So in some sense, that model is inconsistent because there's Brownian motion of the crosslinkers, but not the filaments. But that was the first model we had. And so we looked at the bundling in that case. And then we looked at what happens when the filaments now can also diffuse and rotate. So we don't know yet in our numerical method how to put transverse bending fluctuations. That's what we're working on now. So what we did was we just said, let's assume rigid filaments. And now we know how to do fluctuations. It's just rigid body translation and rotation at each time step. And we looked at what happens when the filaments also diffuse, what happens to bundling. And kind of what we realized was that there's kind of two stages of the bundling process. In the first stage, the filaments are weakly cross-linked. So they're not very cross-linked. They get cross-linkers that bind them together, and they start to come together in these bundles. And basically how that works is you have a cross-linker that binds, it pulls the filaments closer because the cross-linker has a flexible length. So it pulls the filaments closer, and then that allows for another one to bind, maybe down the pair, and it keeps pulling the filaments closer together until it's just a line. They're parallel.
It's almost kind of like a zipper in some sense.
It's a zipper. That's exactly what it is. Yeah. So it zips the filaments together. And so that's in the first stage, you just have these single filaments that are looking for filament neighbors to bundle with. In that stage, Brownian motion is super important because it speeds up the time at which you can find neighbors to bundle. But then there's a second stage where the filaments are highly cross-linked, and they're just kind of, the cross-linkers are mostly responsible for moving them around, rearranging the bundles into one huge bundle. And in that stage, the filaments are basically constricted by the cross-linkers, and Brownian motion is really not that as important. So for instance, we found that in stage 1, Brownian motion speeds things up by a factor of 4, while later it only speeds it up by a factor of 2. So there is a distinction between where you are in the bundling process and the importance of Brownian motion. So that was the first thing that we looked at, was just this result about how does Brownian motion work, how does the bundling process work, and we made this diagram of the two stages. And then the next result that's interesting is about mesh size. So this is what the experiments say, and the experiments are conflicted about this, but they're interesting, right? The experiments say that as you add more filaments, the relative ratio of crosslinkers that you need goes down, right? So if I have 100 filaments, say I need 100 crosslinkers to get a good bundling. If I have 200 filaments, instead of 200 crosslinkers, I only need 180 or something like that. And the question is why? So I think we were...
A one-to-one mapping then of crosslinker to actin?
No, I'm just using fake numbers. I mean, there's some molar ratio in the experiments, but yeah.
But it's not one-to-one.
No, it's not one-to-one. You need many more crosslinkers, right? So, to my knowledge, we were the first ones who actually were able to explain what's going on here. And what we think is going on here is that let's say you have a very small mesh size, a very big mesh size. So you have filaments that are really separated. They diffuse, okay? They're diffusing around, and then boom, all of a sudden they're in contact with each other. If you want bundling, you better be sure that there's a crosslinker there, right? to bundle the filaments together. Because if there's not, then it's just going to keep diffusing around, and it's going to take a super long time till they find each other again.
Yeah, you missed your chance, right? Like it's off into the wind.
So you need a huge concentration of crosslinkers to get bundling in these large mesh size systems. But when the mesh size is smaller, when the filaments are more concentrated, now if you miss, it's okay because you're going to run into a neighbor very soon, another neighbor very soon, and there probably will be a crosslinker over there. So the more dense you go in the filaments, the less relative density of crosslinkers you need to get bundling. That's pretty cool, I think. I think it's a nice explanation.
Yeah, I mean, it's definitely pretty intuitive, right? Like, if you blow your chance asking a girl to prom or something, and one comes right around the corner, you're okay, like, right? But
That's right.
if there's only one girl in your whole town, you're kind of out of luck.
Yeah, that's right. Yeah, that's a good analogy.
So I guess in terms of these like cross-linking and or the cross-linkers and the actin, are there any known byproducts or coproteins that could play an influence in this?
That's a good question. I'm not sure. I mean, one thing that matters is the filament length. So in experiments, they polymerize these actin filaments from actin monomers. And in order to do that, they have something called gelsolin, which I think is a protein, but I don't know exactly what it is. It's a protein that regulates the filament length. And so that's an important, for instance, protein, because that sets the length of filaments in the experiments. In our simulations, what we do is we just have a set length. I mean, we have the ability to do multiple lengths at once, but we never really found it that interesting. What we did look at here was, filaments that are half as long. In experiments, they've been shown to bundle twice as fast. And we looked at, is that something with the geometry of the crosslinkers, or is it just because for a filament Brownian motion, the speed of Brownian motion scales like 1 over L? So bigger filament, smaller amount of motion. And that's all it is. That's what we found. It's just Brownian motion for the length.
Yeah, I mean, the bigger you are, the less a little fluctuation is going to do to you, right?
That's right, yeah.
So are there any other parameters other than the length of the filament, the actin versus crosslinker concentrations that you found to be kind of interesting or have a big influence?
Well, that's what we looked at. So, yeah, I think that's it. I mean, we looked at thermal fluctuations, we looked at the mesh size and the crosslinker concentration, and we looked at the length of the filament, like I said. And the last thing that we studied in this paper was about turnover. So real systems, filaments are constantly polymerizing and depolymerizing. And there's been some experiments that show that when a filament depolymerizes, what happens is that it literally just spontaneously breaks apart. And so what we do is we model it just by removing the filament and rebirthing it somewhere else in the lattice, right? So we remove a filament, remove all its crosslinks, and then we rebirth it somewhere else. That's turnover. That's a proxy for polymerization. And so what you can imagine is that the speed of this turnover, right? So if I have two filaments that are bundling and one of them disappears, then there's no bundling. So there's actually a competition between the time scale of bundling and the time scale of turnover. And that competition sets the steady state structure of the actin mesh that you get. And that was the last thing that we looked at in this paper was, okay, I have turnover, I have bundling. What does my steady state look like? And we showed that it's just a simple ratio of the turnover time versus the bundling time. That sets the steady state structure.
Okay, so just in the model, you just kind of have these two relevant time scales, I guess, in some sense?
Yeah, that's right. I mean, that's basically what it boils down to. We quantify a bundling time scale. Now, that's not trivial to do. We just look at it as the max in the number of bundles. So if you think about it, if a bundle is two filaments, right, then at the beginning, there's a lot of two filament bundles, and the bundle density is at a maximum. and then it starts dropping as the bundles coalesce. And so we consider that peak to be the bundling time. You can use other definitions, but we just found this one to be a nice definition because it also is the rate at which fibers come into bundles. If you fit an exponential to the percentage of fibers in bundles, you get this time scale. And furthermore, we found that it no matter how you define the bundling time, it's really the ratio of bundling times in different systems that controls the geometry. That's really what we were interested in looking at is, okay, I change a parameter, how does the bundling time change? Not as a number, but as a factor relative to the original system.
Interesting. So you kind of already touched on it a little bit, but kind of what's the next step in this to really extend out this and make it maybe even better?
Well, there's really two big things, right? The first one is motors. A lot of people are interested in motors now, and adding motors would be great. And a motor is basically a moving crosslinker. So that's how you can model it. And the speed at which it moves is governed by a force velocity curve. So there's that. But the thing that I'm working on now that I think is really interesting is about adding these bending fluctuations. So it's well known how to do bending fluctuations if you just model the filament as a series of blobs, a series of beads. The problem is if the filament is long and slender, you're talking about 1,000 beads on each filament. So if you want to do 100 filaments, you're talking about 100,000 beads. That's expensive. Part of the benefit of this code is we don't have 1,000 beads. We have filaments that have aspect ratio 1,000, but we can model them with just 16 points, right? And so
I guess just one thing out of curiosity is when you model these in terms of, like the 1,000 bead setup,
yeah,
how exactly do you connect the beads? A harmonic spring and have some type of angle constraint on them to keep it relatively rigid, or is there something special that they do?
Well, so there's just a bending energy. There's a link that connects each spring, and there's a tension in the link which enforces inextensibility. And then there's an angle between the links that gives you the bending energy. And then the force is just
you just have an additional force then, or an additional energy term then in your Hamiltonian.
Yeah.
But I guess the huge benefit of this is no matter what length you do with actin, you can always just use these same 16 Chebyshev points.
That's right. Yeah, I mean 16, 32, 40. 40 is probably the max we're going to go up to. But yes, that's the idea. And so then the question is, we know how to put thermal fluctuations in the discrete setting. So once the fiber's been discretized, if you start with discrete equations, you can add fluctuations pretty easily. There's a way to do it. You have to add, obviously the square root of the mobility matrix. But when the mobility depends on the position, you also have to add what's called a stochastic drift term, which is related to the divergence of the mobility. So the question is, how do we take that to a continuum? And what we're doing now is we are basically taking the discrete model as the truth, which we know the answer, and we're trying to approximate it using continuum curves, using this Chebyshev method. And we'll see how it goes. So I'm optimistic. So far, so good. But we'll see.
Good. So I guess, is there anything? So what was the trickiest part of setting up this model? I think everybody, is at a whiteboard one time really struggling with one particular aspect of something. What was it with this that really took a lot of brain power to figure out?
The tricky part, I would say, is the inextensibility. How do you handle it? So what we actually do is the problem is we have this kinematic matrix. How do I want to put this? So we know that there's a set of possible motions that the fiber can undergo because it's inextensible, right? It can't stretch. So we parameterize that space of motions, which is all well and good. But the problem is that when you write discrete equations, and if you just move by delta t times the motion, you're still introducing some air in the inextensibility. And what happens is if you have crosslinkers, that air builds up and you get fibers which really stretch. So the idea that we had was instead of just updating the fibers in a linear way, so solving for velocity and then updating, what we actually do is we take the velocity, and from that we compute a velocity, an angular velocity of the tangent vector. So if the fibers are parameterized by arc length, the tangent vector has unit length, right? So it lives on the unit sphere. So we compute a rate at which that vector is rotating, and then we actually do the rotation on the unit sphere. So we rotate the tangent vector to keep it exactly of unit length. And then we just integrate to get the position. So from xs, derivative, you integrate that, you get x. So that was kind of the hardest part, is keeping those filaments.
More or less, you kind of shrink it down to a unit vector, you rotate the unit vector, and then you expand it back out?
Well, no. What you're thinking about is x is the fiber, right? And then tau is the derivative of x. That's the unit vector. So that's also a function of where you are along the curve. So at each point along the curve, you have some velocity of the tangent vector. You take that tangent vector and you rotate it. So now you have a function along the curve, which is your new tangent vectors, all of which have unit length. And then you just integrate that function to give you a position. So it's not that you're shrinking the fiber down, you're looking at the tangent vector at each individual point.
Ah, interesting. I was kind of thinking it was more, if you have a matrix, you find more or less where you find an eigenvalue that only rotates it, and then you find the eigenvalue that kind of expands it back out. It's more like a singular value decomposition than approach, but this is completely different.
It's different. It's more just based on calculus, right? It's based on the fact that I need to keep that tangent vector of unit length. That's the constraint, and we want the constraint to be preserved exactly numerically. And to my knowledge, our method is the first one, and this is like, the first one to do a bunch of different things. So it's going to sound like not much of an achievement, but we're the first one to use continuum curves and keep the inextensibility constraint exactly. So other methods that have continuum curves, they have a penalty in their equations. And that penalty can sometimes affect the time step that you can take, which is not good. So
yeah, I mean, if you have like you said earlier, the stiffer the spring constant, the smaller the time step you have to take. So
exactly. So we don't have to worry about that.
Is there anything super surprising in terms of the results that, when it kind of showed up on the screen, you're like, whoa, was not expecting that?
I don't really think so, and that's why actually one of the reviewers said that our paper didn't have provocative enough results. I think this is not in this paper, but it goes back to a previous paper. The question of, if you try to move a bundle and you add hydrodynamic interactions in the bundle, the stress goes down. So basically the work you need to do to move a bundle goes down when you account for interactions between the filaments. And that was kind of surprising to me, because in work originally we looked at just filaments that are uniformly distributed, and we found that when you add hydro, stress always goes up. So why was this stress going down when bundles are moving? And the reason is, we thought about it, and the reason is that filaments work together when you move a bundle. So you have 2 filaments, 3 filaments in a bundle. When one filament moves one way, it creates a disturbance flow that pushes the other filaments the same direction. So the disturbance flows are working together, and so the amount of work that you really have to do goes down because those disturbance flows help you. And this is the opposite of forming a bundle, where I talked about that earlier, that the disturbance flows hurt you because they drive the filaments in the opposite direction that they're moving. So that was, I think, the most exciting result that we had.
This is kind of like if your close friends do something, you're going to do it, but if someone that you barely know does something, you're more likely to kind of not do it.
Yeah, I guess. Yeah, that's
peer pressure at the actin filament length as well.
Yeah, that's a good explanation. I like your explanation about the prom, though. I'm definitely going to use that in my talks.
Um, so I guess kind of wrapping up, is there anything else that you kind of want to add or talk about?
Well, I want to thank my advisors because I couldn't have done this work without them. So it's Alex Donev, who's they're both in the math department, but Alex is just in the math department. And then my other advisor is Alex McGillner, and he's also in the math department, but also in the bio department, both at NYU. And they've really made my PhD so much fun. So I really appreciate them.
That's good. And I guess kind of the last question I have then is, so where do you see this in maybe 5 or 6 years? Where do you see the progress?
Yeah, in 5 or 6 years, I see myself trying to make a model of cell division, trying to use all these ingredients to come up with a macroscopic model of cell division. So we already had a paper where we took this complicated gel and we looked at, can we just make it a Maxwell, can we just make a generalized Maxwell model of it? Throw a couple time scales, and now we can write a continuum PDE. It's a complicated PDE. I don't think it's linear. That represents that motion of that fluid, which is this gel. And so using that kind of approach to model cytokinesis would be really fun.
Interesting. So you're taking all these little building blocks, I guess, that you've done throughout the time and kind of building it all into, the mega model.
Yeah, building into a mega model, and probably it's not going to be feasible to do an agent-based model. Then we'll have to write, at least for this gel, we'll have to write a continuum equation. And maybe just represent the gel on the membrane, because that's what's driving cell division. Maybe use agents for that. But it's a long way off, so we'll see.
I mean, yeah, but yeah, super interesting. Andre, thanks for being on the show.
Thank you. Thank you very much.